Have you ever really stopped to think about what's going on inside a battery? I mean, we know they make our phones and remotes work, but how? How do they create that nonstop electrical push? It's not just a single shove. It's this relentless, continuous force. Well, today we're pulling back the curtain and uncovering the secret life of a battery. Let's get into it. So, this is the central mystery we're going to solve together. Why does a battery push electrons continuously? Think about it. It doesn't just give one big jolt and then stop. It maintains this steady, constant pressure that keeps the electricity flowing. How on earth does it do that? That's the big question for today. And here's our roadmap. First, we'll uncover the invisible force that's doing all the pushing. Then, we're going to figure out how to measure that push. We'll also clear up a super common point of confusion about which way things are flowing. And then, the best part, we're going right inside the battery to see what makes it tick. By the end of this, you're going to get it. Okay, let's start with part one, the invisible push. Before we can understand the battery itself, we need to understand the fundamental force that gets everything moving in the first place. So the second you hook up a wire to a battery, something amazing happens. The battery creates this invisible field of influence that stretches through the entire wire. You can kind of think of it like a dry riverbed that suddenly has a powerful current flowing through it. This is the electric field, and it always points from the positive terminal to the negative one. Now, this field isn't just for show. It exerts a force, we'll call it F sub E, on any free charges hanging out in that wire. And here is a super important tip, especially for your exams. Electrons are negatively charged, so the force on them is actually opposite to the direction of the field. So the field points from plus to minus, but the electrons get pushed from minus to plus. Seriously, write that down. It's a classic trip-up. So this force, it does work. It physically shoves the electrons and moves them through the wire. When we say work is done, what we really mean is that energy is being transferred from the field to those electrons, giving them the get-up-and-go energy to flow. So we have this invisible push doing all this work. But how strong is it, right? How do we actually put a number on it? Well, that brings us to our next section. This is where potential difference comes in. You probably know it by its more common name, voltage. It's actually a really simple idea. It's the amount of energy the battery gives to each individual packet of charge. Think of it this way. If work done is the total energy needed to move a whole crowd of people, potential difference is the amount of energy given to each single person in that crowd. And here's the formula that ties it all together. V, for potential difference, is equal to W, the work done, divided by Q, the charge. It's literally just energy per charge. This is one of the most fundamental formulas in electricity, so you've absolutely got to know it. We measure this in volts. So next time you pick up a 1.5 volt AA battery, you'll know exactly what that means. It means that battery does 1.5 joules of work for every single coulomb of charge it pushes around the circuit. See how it connects energy and charge so perfectly? It's not just a random number. All right, let's talk about something that trips up so many students year after year. We know the electrons are moving, but which way do we actually say the current is flowing? Let's get this sorted out once and for all. Okay, look at this breakdown. On the left, you've got conventional current. This is an old idea from before we knew about electrons, and it assumes that positive charges are the ones moving. So it flows from high potential, the positive side, to low potential, the negative side. But on the right, you see what's actually happening. The real electrons flow from low potential, the negative terminal, to high potential, the positive terminal. Now, for all your circuit diagrams, for all your exam problems, you are going to use conventional current. But in the back of your mind, you need to know that the little electrons are actually racing in the opposite direction. Now, speaking of what's moving, it's not always electrons. What carries the charge really depends on the material it's flowing through. Let's compare two different scenarios. So in a simple metal wire, things are pretty straightforward. The positive bits, the nuclei of the atoms, are locked in place. The only things that can actually move around are the free electrons. But in electrolytic fluids, like the chemical goo inside a battery, it's a whole different story. In there, you've got both positive ions, called cations, and negative ions, called anions, and they are both free to move, swimming in opposite directions. This is so important for understanding how a battery actually works. Which brings us to the main event. Let's finally crack open that battery and see what the engine room looks like. How does a battery create, and more importantly, maintain that potential difference? Inside that battery, there's a constant battle between two forces. First, there's a chemical force, F sub c. This comes from chemical reactions in the electrolyte, and it literally sorts the ions, pushing the positive ones to one metal plate and the negative ones to the other. Now, as these charges start piling up, they create their own electric field, which creates an opposing electric force, F sub e, that pushes back. So the chemical force keeps pushing and pushing, while the electric force pushes back harder and harder, until, finally, the electric pushback is just as strong as the chemical push forward. At that exact moment, Fc equals Fe, everything comes to a standstill, and you have a stable, constant voltage between the two terminals. Okay, so the battery is sitting there, fully charged, its internal forces in a perfect standoff. What happens the instant we connect a light bulb and close the circuit? And this is the secret to the continuous push. The moment electrons start flowing out of the negative terminal and into the positive one, that perfect balance is broken. The pileup of charge on the plates goes down a little, which weakens the electric force, F sub e. And suddenly, the chemical force, F sub c, is stronger again. It immediately kicks back into gear, pushing more ions to the plates to rebuild the charge and get the forces back into balance. It's this incredible, self-regulating cycle that just keeps going, always fighting to maintain that constant voltage. So here's the bottom line. The reason a battery eventually dies isn't because it runs out of charge. It's because the chemicals that create that chemical force, they just get all used up. Once that chemical reaction stops, the push stops. Simple as that. Okay, lightning round, exam recap. Let's lock this in. 1. Potential difference is just energy per charge, V equal W over Q. 2. The unit is the volt. 3. Don't forget, the electrons flow from low potential to high potential. And 4, the battery's secret weapon is that constant battle and balance between the chemical force and the electric force. Nail these 4 points and you are golden. And that leaves us with one last thing to chew on. We've just proven that a battery provides a constant push, right? A constant voltage. So what actually determines how fast the electrons flow? What controls the amount of current in a circuit? Well, that's a fantastic question and the topic for our next explainer. Thanks for tuning in.